So let's look at another example here of a related rates problem. And I still see that that exciting cube that I was able to expand. That made me really happy. Okay, so the next example, example 3, is dealing with a snowball, and we sort of have to assume that the snowball is perfectly spherical. And it says spherical. Okay, so that's good. Now, and then the thing you should also know is that, I mean, technically, I guess you could be expected to know that formula. And at one point, if you look at the history of the AP exam, at past questions, you students did need to know that formula. But in years past, it's also been like a trend that they will give you that formula. So you should know it, but most likely they probably will give those to you. And something obscure like cones and pyramids, I would definitely give those to you as well. But okay, I'm sorry, excuse me. So the things you should know about a sphere, just kind of going into it, the volume of a sphere is 4/3 pi r cubed. And then surface area, if you ever need that, is 4 pi r squared as well. Okay. Or I mean, like in addition, that's the other formula. Okay. So a spherical snowball melts so that its surface area decreases at a particular rate. Find the rate at which the radius changes when the radius is 10. So it's talking about surface area. So that seems to be the one I want to start with. So surface area equals 4 pi r squared. And I need to introduce time, so I'm going to d dt both sides. So that means that this becomes the derivative of surface area with respect to time. So derivative of surface area with respect to time. And remember, r's are variable, so the 2 comes in front, so it's 2 times 4 is 8 pi constant r, and then dr dt. And so again, I like this label. It's a rate. It's the rate that the surface area is changing with respect to time. This is the rate the radius is changing with respect to time. And they give us a value of 30, which is already appropriately labeled. So 30 centimeters squared per second. That's the surface area. So I could say 30 here. I could even say centimeters squared per second. But I want to make sure I include is that it's decreasing. If it's decreasing, you need that negative value. Equals 8 pi when the radius is exactly 10 centimeters. So what I must be looking for is the rate at which the radius is changing. So I'm looking for dr dt. So I'm going to sort of solve for that variable. Well, I know 8 times 10 is 80, and they have 80 pi centimeters. So I'm going to divide that across. I have a space here. So I've got negative 30 centimeters squared per second divided by 80 pi centimeters. And what I like is that this centimeters would cancel with one of those centimeters, and that will be the right dimension for dr dt, because our radius is a linear measurement, so our value should be linear. So negative 30 over 80, that's like negative 3 over 8. Hold on to your pi in the denominator, right? That's still there. Centimeters, just that 1 centimeter per second. Centimeter per second, which would be the rate that the radius is changing with time. Now, I like that I called that negative, but I could also, right, because it says find the rate at which it's changing. So the negative is important. Or you could say it's decreasing by the rate of 3 over 8 pi. But make sure you include the correct label. Okay, now another example with a sphere. This one a balloon. It says it's deflating at a rate of 6 cubic centimeters per second. And already I'm paying attention to the context, right? Like cubic centimeters, that's volume, all right? And so I want to start with my volume of a sphere formula, which we said was 4/3 pi r cubed, and I want to introduce the element of time. So I'm going to d dt both sides. Oops, I already had that. Okay, so d dt. So that allows me to get dv dt on the left. Oh, back to blue. So it's 1 dv dt equals, and then this 3 comes in front of the 4/3, so it basically is a 4 pi r squared, and then immediately multiply by dr dt. So we have the two rates. Now, funnily enough, this is a little bit familiar, right? 4 pi r squared, that's surface area. So it's kind of, I think, ironic or interesting, the connection that the derivative of volume of a sphere, which is 3 dimensions, is equal to the surface area of a sphere, which is 2 dimensions. So I thought that was kind of cool. All right, now let's start putting things in. It's deflating, so we're thinking decreasing at a rate of 6. So I could call that -6 centimeters cubed per second is equal to 4 pi, and then the radius at that particular instant, 4. So times 4 centimeters squared, and then we must be looking for the rate that the radius is changing, so dr dt. So I have -6 centimeters cubed per second equals, and if I square this out, that's 4 is 16 is 64 pi, and then it's centimeters squared. And then I have my dr dt. So I'm going to divide that across, and again, the right label should emerge if I did that correct in terms of the units. So that cancels, and so centimeters squared will go into that 2. Centimeters squared will cancel all but one of those. And then I've got like a 6 to 64, which is equal to, I'll come up here, divided by 2, -3 over 32 pi. And then that's centimeters per second. And that's my dr dt, the rate the radius is changing. So I can leave it like that, or I could say it's decreasing by that vectored amount, or the scalar amount of 3 over 32 pi. Okay, so spheres, in circles are very common things that would be changing over time in terms of a problem on unrelated rates. But in the next video, we'll look at other things that could be changing as well.